For problem number 3, we are working with a solid conducting sphere carrying charge Q. The key here is that it's a conducting sphere. So if it has charge Q, then all the excess charges go to the outside of the sphere. And that leaves the net charge on the inside of the sphere equal to 0. So when we're talking about electric field at distance r, where r is less than a, if I have a distance less than the radius of the sphere, so this is my radius r, then we want to look at the equation that the electric flux is equal to EA, which is also equal to Q enclosed over epsilon naught. The enclosed charge in a conducting sphere is equal to 0. So Q enclosed is equal to 0. If this is 0, then our electric field, if I solve for the electric field, is also 0. So there's no electric field inside of a conductor. Now, if we were to look at the electric field outside of a conductor, and we're going to call this R, then we are going to use, so this is for part B, our electric flux equation, EA is equal to Q enclosed over epsilon naught. Our area is going to be the area of our Gaussian circle or sphere, which is the surface area 4 pi r squared. Our enclosed charge is the entire charge of our internal sphere. And then epsilon naught's just a constant. So if I'm trying to solve for the electric field here, I'm just going to divide the 4 pi r squared to both sides. And I'm going to rearrange it so that my 4 pi epsilon naught is together, because I know that that equals K. And I can simplify this down to KQ over R squared. And as I mentioned in class, this is the electric field for a point charge, and that would be the equation that you derive using Gauss's law, whether it is a conductor or an insulator, as long as your Gaussian sphere is on the outside, then you would get this as your equation. And you can treat it again, like I said, as a point charge. So let's go ahead and graph this. Since I know inside of the sphere, I have 0 enclosed charges, no charges in the center. Anything below a radius of A is going to be 0. Once I hit the surface, I'm going to get a electric field, and in this case, it's going to jump up to an electric field of, let me write it down. If I just plug in A here, R equals A, it will be KQ over A squared. Now that's going to be my maximum electric field, and then you can tell by the relationship between the electric field, electric field and the radius, they are inversely squared proportional to each other. So as the radius increases in magnitude, the electric field will decrease by a factor squared, which means it gets closer and closer to 0 as it goes out to infinity. So this is what your graph is going to look like. Again, your maximum is going to be when R equals A, and then everything exponentially decreases to 0.